Another special factoring pattern that you want to be aware of is in this left-hand column now here. So all these expressions in the left-hand column are in completely factored forms. What you're seeing is like each particular factor really uses the same terms, but one has a plus and one has a minus. So what we usually denote these types of factored expressions as is we denote them as products, and the reason why we have the word product there is because you are producting, different sorts of expressions with one another. But really what you are doing is you're doing a product of a sum and a difference of the same terms, but usually we just say the product of a sum and a difference. And when we say a sum and of a difference, really what we're referring to is like whatever the plus version of the expression is and the minus version is, that corresponds to what is the sum and what is the difference. So in terms of like actually foiling these sorts of things out, if I take like the middle example right here, when you do the 4x times the 4x, you get 16x squared, and then 4x times 3 is plus 12x, but you'll have a minus 12x, so that ends up canceling out in the middle, of course, so you really then just get just the minus 9. So that's actually going to happen with all these examples right here, is that you cancel out the middle terms. And so if we look at this just very generally, if you do have something that we denote as A, and then if we have something that we denote as B, but one's a plus and one's a minus, really what you will get as a result out of that is you're just going to get the A times itself, and then a subtraction of what the B is times itself. So A squared minus B squared really will always factor as A plus B times A minus B. And so you can kind of see that with the example that we had just seen with the 4x minus 3 and the 4x plus 3, because if you treat like this 4x right here as really like your A, you can see that then when it got multiplied out, like this really is what the A squared is right there, right? It is the 4x times the 4x. And then you can also see that if you treat this 3 right here as your B value, then that right there really is your B squared, and so you do have something of the form A squared minus B squared. So when things are of that form, A squared minus B squared, or you can write an expression of that form, then we want to be able to know how to factor that. And so it turns out that in these examples, in these three boxes right here, we want to try to identify if they are of that form A squared minus B squared. So with that very first example right there, you can see there is no middle term, no middle x term. You just have the x squared term and then just a constant. So you can see that they're both perfect squares. So if you think about this first term right here as being like 8x times 8x, and then you treat the other expression as 7 times 7, then you can clearly see that you do have basically some sort of an A, which really is the 8x squared, and then you can have the 7, you treat that as your B, so really you have something of the form A squared minus B squared, which then tells you that you should be able to factor this as basically like an A plus B times an A minus B. But if we substitute in what our A actually is, it really is just 8x. And then if you substitute what B is, it's just a 7, and then one's a plus and one's a minus. And it does turn out that then this right here is the correct factored form of that. Because if you do FOIL that out, you're going to get 64x squared. The middle terms are going to cancel out because you're going to have plus 56x and minus 56x, and then the 7 times negative 7 creates that subtraction of the 49 at the tail end of that. So the rest of these expressions are all pretty much the same. You could probably really just kind of figure it out, like this has to be 2x times 2x and negative 13 plus 13, and of course you're going to cancel out the middles, and then you do get your 4x squared and then the minus 169 going on there. And then this one ends up being 6x plus 1 and 6x minus 1. So that's a little insight into factoring of difference of squares. So some things to also kind of think about a little bit at the bottom right here. So when you look at 18n squared and minus 800, you can see that there is no middle linear term. Now, 18 and 800, though, aren't perfect squares or anything. So when we're thinking about factoring, you should always be thinking about GCF first. And in this case, there is a GCF of 18 and 800. At least there's a 2. If you take out a 2, you need to be left with 9n squared minus 400. So yeah, I think 2 is the largest GCS out of that. And then if you take a look at that expression right there, which is 9n squared minus 400, it does turn out that 9n squared is a perfect square because it's 3n times 3n, and then also 400 is 20 times 20. So you're able to actually factor that further, and you can factor this then as 2, and then break it down to 3n minus 20, and then also a 3n plus 20 factor. And then that gets broken down all of the way to just linear factors along with that constant of 2. So that gives us that. And then if we go over to the example next door, 12 and 27 have a 3 as a greatest common factor, and then you can also take out a g squared. And so from there, you're going to end up with like a 4g minus a 9. And then you look at, okay, so right here, like 4 and 9, right, like they're both perfect squares, but the thing is, though, is that the g is not a perfect square, right? Because what you actually have right there is you have a linear term, and you can't break a linear term down any further whatsoever, right? And so that right there actually gives you your completely factored form for that particular expression there.